is on switching between mixed and entire radicals. But this time, we may have variable parts to those radicals. Okay? Whereas in 10C, when we're working with radicals, everything is numbers. Okay? So for example, convert each mixed radical to an entire radical. Apply the concepts to the expressions involving variables. So essentially, we're just going to use what we already know to try and write an entire radical here. Okay? So this is like a simplified expression, a mixed radical, j times the square root of j. So if you think about the simplification process, if there's a j on the outside for a square root, how many j's would you have had to have on the inside to pull that out? An extra 2, right? So this is going to equal, oh, come on. This is going to equal the square root of j, that's the first one, times j times j. Okay? Or sometimes people write it this way, j times j squared. Looks like a y squared. Let me fix that. In between. Right? You can do that too. And here it's just kind of indicating, okay, I'm putting the one on the outside back inside twice. Either way, all together, you've got the square root of j cubed. Okay? All right, let's look at this guy. There's a k to the 4 on the outside. We're looking at a cube root. How many k to the 4s would we have had to have on the inside? 3. So I can start out by looking at the cube root of, this is what was already in there, 5k squared. And then I got to put k to the 4 times k to the 4 times k to the 4 back on the inside, right? Now at this point, we need to simplify. So here's where we're going to apply our exponent laws. Okay? This would be a product rule. So we've got the cube root. The coefficient is 5. And then 2 plus 4 plus 4 plus 4, that is 14. Yep. Oh, yeah, we're good? OK. All right. So sometimes people put them in this way where you put 3 sets of them in. That's totally fine. Here we have a 2m on the outside. We're taking the 5th root. How many times do we have to put that 2m back? 5. So the other thing you could do is put it in this way instead of having to do that repeated multiplication. So you can do that too. You just have to remember your power of a power rule now when we simplify, right? So this is going to be the 5th root of 3m cubed. And then this exponent of 5 applies to the 2 as well, times 2 to the 5 times m to the 5. Okay? And then we simplify that. So 2 to the 5 is 32, times 3 is 96. So we're looking at the 5th root of 96, and then m cubed times m to the 5 is m to the 8. Okay? And the sort of expectation is that you do use exponent laws to simplify the radicand on the inside, or the radicand expression. Okay, so that's going from mixed to entire. When you are going from entire to mixed, okay, what you want to do is essentially either expand the exponent or the powers on the inside, or visualize the expansion. Okay, so if I'm looking at the square root of 13, I'm looking at the square root, or sorry, the square root of x to the 13 rather, of x multiplied by itself 13 times. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay? And every time I have a pair of x's, because this is a square root, I can pull one of them out. So if I circle my pairs, I've got 1, 2, 3, 4, 5, 6 pairs. and then 1 left over. So this is going to simplify to become x to the 6 square root of x. Okay? Now, you do not have to do this step in the middle, because a lot of people can visualize, okay, I need pairs of x's. If I've got 13 altogether, I'm going to have 6 pairs and 1 left over. Okay? That's fine. This guy. Let's actually try and imagine this one without having to expand it out. If we visualize what this, the 4th root of c to the 7 looks like expanded, firstly, what's our group size do we want? 4. So if we got 7 of them, how many groups of 4 do I have? 1. So I can pull 1 out. How many are left on the inside? 3. Yeah, so this is going to be c times the 4th root of c cubed. Okay, and if this is a stretch, no problem doing the expansion, right? So the other, what this looks like expanded is 1, 2, 3, 4, 5, 6, 7. Here's one group of 4 that can come out, and then there's 3 left on the inside. Okay? All right, so we've got the cube root of a squared b to the 7. Okay, so if we're looking for cube root, we need groups of 3. Do I have a group of 3 a's? No, so I actually can't do anything with that a squared. That's going to be left inside. Do I have any groups of b's? Yes, how many? 2 groups of 3, and then how many are left? 1. So I can pull out 2 b's, and then there's the a squared left and the b left. Okay? Now I'm looking at the square root of 40y to the 13. So you need to simplify the square root of 40 as well, right? So there's where you're thinking like prime factorization. Yes?
So if you were doing that, would you end up getting something like, if you have are they like two, do you think of them as 2 separate? Because I think
Yeah.
y6 and like 2y6 square root of 10y?
Almost, except I believe, wait. Oh no, yeah, you're right. For some reason I thought that 16 was a factor of 40. But it's not. Yeah, exactly. So if you could do that in your head, great, right? If not, some people especially need to think about the prime factorization of 40. So 40, right, is like 2 times 20, 2 times 10, 2 times 5, right? So at the very least, you may need to expand this part and do the other part in your head. That's fine too. 2 times 2 times 2 times 5 times y to the 13, right? So you can do a combo too. You do what you need to do to know that you're correct, right? And then we can pull out one of these, and we can pull out 6 of these, right? Because there's 6 groups of y squared. So we're going to end up with 2y to the 6. And then on the inside, what's left here is 10. And here there's 1 extra y. OK, so far so good? All right, so next thing that we should discuss, and in fact, we already discussed it a bit in 10C, is that when you multiply 2 radicals together, as long as they have the same index, you can write it as a single radical, right? Now, in 10C, we usually actually go in this direction where we take 1, and we maybe split it up so that one of them is a perfect square or a perfect cube or whatever you're dealing with, right? That's kind of the 10C direction. In 20-1, we usually actually go the other way. So we talk a lot about how do we multiply radicals together, okay? Now, when you go this way, what often happens is you may start out with 2 radicals that cannot be simplified. But when you multiply them together, the product, the radicand, which is the product of the 2, can be simplified. Okay? So for example, let's say I have 3 square root 10 times 5 square root 2. Okay? Now, can't simplify the square root of 10. I can't simplify the square root of 2. But when I multiply these together, 3 times 5 is 15, times the square root of 10 times 2 is 20. This can now be simplified. And so I have to think, okay, 20 is 4 times 5, so I can pull a 2 out. And there's a 5 left over. And if you need to do prime factorization to get from here to here, that's totally fine. And so all together, I have 30 square root of 5. Okay? So we're going to practice this a bit. We'll do it with numbers and with variable expressions as well. And in fact, we'll do like maybe 2 of these. And then I'm going to get you guys to try, let's do like, I don't know, D over here and B together. And then I'm going to get you guys to work on the rest of them on your own. Okay? Yes?
Sorry, can you cover what we were supposed to do for like roots that aren't 2? You just
So if you're taking a cube root, for example, yeah, so if you're taking a cube root, then you want 3 of the same factor.
No, but like for that you multiply.
Oh, yeah. So exactly, yeah. So as long as the index is the same,
Okay.
you can
So
multiply
if
the
index is
radicand.
not the same.
Yes.
Okay. But
You
just
cannot.
don't add them together or anything.
No. So you can't do this. If you have like the square root of 2 times the cube root of 2, whoops, or even the cube root of 5 or whatever, okay, can't do anything here. Can't simplify further. Right? Because one of them is a square root, one of them is a cube root. Okay? As long as the index is the same, though, we're good to go. Okay? So let's maybe do one of these together, do 2 of them together, and then we will do the rest. You guys can work on the rest. Okay? So here we're looking at 2 root x times 5 root y. So we multiply the outside together. 2 times 5 is 10. And we're looking at the square root of xy. Okay? Now, when you're doing something like this guy, okay, 3 square root 5x times 4 square root 15. Okay? We're going to multiply the outsides together. We're going to multiply the insides together. And when I multiply the insides together, what I often like to do is actually not make this like 75x squared, but expand it. Because then it's really, really easy to simplify after, right? And it tends to be easier to prime factorize smaller numbers than if I multiply these together anyway, right? So 3 times 4 is 12. Then I'm looking at the square root. I can't write that down anymore. 5x times, this is 3 times 5 times x, right? Now I can immediately see the pairs. I've got this pair and this pair. So I can pull one of those out, and then I've got the 3 left on the inside. And it's just, I find that to be really quick. On the other hand, if you make this 75x squared, a lot of people can do that in their head too. So it doesn't really matter, but so this is going to be 60x square root of 3. What happened there? Okay, you could absolutely do this. 12 square root of 75x squared, right? And then think, okay, 75 is like 3 times 25. 25 is perfect square, so I can pull a 5 out, left with a 3. And then this is, if there's two x's, I can pull one of them out, right? That's fine too. Okay. For something like this guy, I find it's like either or, they're kind of the same. But sometimes when you get like a really long string of prime factors or factors of variables, this strategy can be helpful too. Okay? So I'm going to give you guys, how many have we got here? Are there any more on the next page? Nope. I'm going to give you guys like maybe 10, 15 minutes to work on these. If you want to start working on these problems on the next page, you can do that too. We'll go over those next. First, express the side length of this square as a radical in simplest form. Okay, this is a square. If the area is 12x cubed, centimeters squared, how could we figure out the side length? Yeah.
The first thing you would do is you know that put an x outside.
Okay, so but what are yes, you're almost 2 steps ahead. Yeah?
Okay, so the area is the root or the side length squared, which means
Exactly.
that in order to get the side length, you need to
Yeah.
get the square
Yeah.
root of the area.
Totally. So when you're looking at a square, right, with side length x, that will have an area of x squared. Okay, so if you know the area and you want the side length, you need to take the square root. Okay, if you know the side length, you want the area, you square it. Okay? All right, so to get the side length, s, we are going to have the square root of 112 x cubed. That's correct. Okay, and then to simplify that, we want that in simplest form. So the 112 is, what is that? 4 times something.
4 times 2. Yeah.
It's 4 times 28, right? No? Hold on. Because it's 4 times 25 is 100. 4 times 3 is 12. So it should be, it's 4 times 25 plus 3, 28. Doesn't matter. We can do prime factorization to make sure. Right? This is 2 times 56, 2 times 28, 2 times 14, 2 times 7, right? And in fact, just looking at this, there's 1 pair of 2, 2 pairs of 2. So I can pull those out. And then how many x's can I pull out? 1, because I have 1 pair, right? And then there's going to be 1 left over, and this is left, 7x. So that's 4x square root 7x.
What will we do with that, sorry, if we were given this question? Is that just where we stop?
Yeah, that's an expression for the side length of the square. Yep. Okay. Okay, so this is a nice question. A cube has a volume of 2,000 cubic inches. What's the surface area of the cube as a radical in simplest form? Okay. So what would be a good place to start here, do you think? Yeah?
Cube root of 2,000.
Okay, you could start with that. I would even start by just drawing it, because we're looking at a cube in terms of its volume and its surface area, right? So I mean, listen, if you don't need to do this, that's fine, right? If you can visualize it, that's fine. But I personally like to draw this, right? So we know that the volume of this cube is 2,000. Yep.
Could you do something along the lines of like 2,000 cubic inches divided by the cube root of 2,000 cubic inches?
No, so 2,000 cubic inches divided by the cube root?
Yeah.
No, you couldn't. Because that would give you, okay, well, if you know that that is,
Is that
oh, I see, because you're after the surface area. Yeah, let's come back to that. I like that. I never even thought of that. Yes?
So, sorry, this is kind of a shot in the dark, but do you, because you know that the one side length is the cube root of the total
Yeah.
volume, right? So you do the cube root of x to the power of 2 in order to get that surface area, right?
Yes. So yes, and a lot of you guys are thinking along this lines. What I like to do with this type of question is almost do a roadmap, right? So if I look at the volume, that's x cubed. What's the surface area in terms of x of a cube? What's the area of one side?
Oh, not PSA, okay.
What's that? X squared. And how many sides are there? 6.
Oh, so it is total surface area. It's not just the surface area of one side.
Right.
Okay.
Yes.
So
So what we need to do here is use the fact that we know the volume to figure out x. Once we know x, we can figure out the surface area.
So I have,
Yes. We're going to get back to yours in a second. Okay? All right. Yeah. Yeah, you can do it that way. All right, so we have 2,000 equals x cubed. So x is going to be the cube root of 2,000. Okay? Now, you could, at this point, do prime factorization, and that's fine. But some of my cubes and squares and whatnot, I just remember. And I know that 10 cubed is 1,000. And 2,000 is 1,000 times 2. So I know that from the 2,000, I can pull a 10 out, right? Of course, if you need to, you can take a few more steps to get there. But I can see that you guys have got that step down, so that's all good.
if it's 2 squares, you just multiply 10 by 2. Because it can't be brought down further.
So are we going to multiply 10 by 2? No, like this 10 comes out because in here you've got cube root of 1,000 times 2, right? And cube root of 1,000 is 10. Okay, so once we have x, we know that the surface area is 6x squared, which is 6 times 10 cube root 2 squared. And that is 6, this multiplied by itself, times 10 cube root 2 times 10 cube root 2. Okay, and now at this point, we're just multiplying the numbers on the outside together and then multiplying the two radicands together. And it's already simplified. Right? So 6 times 10 is 60 times 10 is 600. Cube root of 2 times 2 is 4. Centimeters squared.
Inches cubed.
Oh, shoot. Inches cubed. Squared. It's surface area is an area. You're right. Okay. Inches squared. Okay. Now, I think what you were talking about, which I didn't think of doing it this way, but if you think of right? X squared. So I think what you were thinking about is I want to get an expression for x squared.
Well, yeah.
Because if I know x squared is, I just multiply that by 6. Is that where you were?
Because I had like 2,000 divided by 2,000 cubed times 6. Then you've got
Right? So where does this come from? What you were doing, which is really kind of cool, this is actually x cubed over x. And that's your x squared. So if you can simplify that, you just pop that in there, and then you don't have to square it anymore. Now, how do we do this? Now, I have to say, that's a really creative way of doing it, but I probably wouldn't expect most people, including myself, to come up with that, right?
That was just my first thought.
Oh.
I didn't see the other way.
Okay, now that's fine. How do we simplify this though? You have to think about this in terms of a power and then think about your quotient rule. So this is actually 2,000 to the 1 over this is 2,000 to the 1/3.
Okay.
Right? And then you subtract 1 minus a third is 2/3. And that is actually equal to x squared. Or it's the cube root of 2,000 squared. So if you put that in there and simplify, yes, you will get the same answer. Okay? So what you are doing, instead of saying, let's get a value for x and work with that, you thought, let's get a value for x squared and work with that, because that's what I need for surface area.
Yeah.
Right? Yeah. You can do that, and then you just take this, pop it in there. Replace x squared with 2,000 to the 2/3. Yeah. That's cool.
I'm sorry, that's literally the only thing that was my first time.
Okay.
Well, it's just like, that's just how I saw it.
Okay. I learn something new every day.
Sorry.
No, I love it. I love it. Okay. C. Okay, so the largest square in this diagram has side length 16. Calculate the side length and area of each of the two smaller squares. Okay, so what do we know? These are all squares, and this is 16, and this is also 16. Yes? Uh-huh, you sure can.
There's another way to do this one.
Okay.
It would be, each square is half of what it was before. So if you've got your total, are we looking
Yeah, so that'll give you, okay, each square is half of what it was before. Let's go to that next, okay?
Technically, wouldn't it not be? It just looks like that on the graph. Or the-
It is half of what, because essentially, like if you do this, right? Okay, this is half of that, and this is half of that, and this is half of that, and this is half of that. Yeah, so you're right. Yeah, that's actually really cool. I didn't think of that either. But let's work with Pythagoras, because I think that's probably where most people will go, including me, when I did the completed notes and put them on D2L. Okay? So if we work with Pythagoras, if it's a square, this is a right angle, right? What are each of these side lengths? 8 and 8, right? So this, if I call this guy x, I'm going to have x squared equals 8 squared plus 8 squared. So, which is, well, it's 64 plus 64. So it might actually be handy here to write this as 2 times 64. The reason for that is that we need to take the square root of it. And if we write it this way, we've already got the perfect square factor, right? So x is going to be the square root of 2 times 64, and this is 8 times 8. So that's 8 square root 2. Okay? And of course, you could absolutely 100% write this as 128, do prime factorization, you will get the same result. Okay? All right, let's try and look at the side length of this guy over here. Okay? Now, this whole thing is 8 square root 2. How much is this part going to be? Yes? 4. It's, no. So think about it this way. Like radicals are almost like variables. I have 4 root 2s, or sorry, 8 root 2s. If I cut that in half, how many root 2s am I going to have? 4. Yeah. So this part is 4 square root 2. And this part here is also 4 square root 2. And so if I want to know this yellow piece, let's call that y. Okay. Then what I'll have is that y squared equals, why did I put a line where?
Minus in front of y, 2.
Oh, because I just touched it. It's not.
Oh, okay, thank you, sorry.
Yeah, no, it's all good. 4 square root 2 squared plus 4 square root 2 squared. Okay. Now here, let's just talk about what would this be? 4 square root 2 squared. Not quite. Almost 4 times 2. Yeah.
Would it be 16 times
Yes.
square root 4?
It's 16 square root 4 or just 16 times 2. Yeah. So this is going to be 16 times 2 plus 16 times 2. Right? Because I'm squaring 4, which is 16. I'm squaring root 2, which is 2. And that is 32 plus 32 is 64. So y is 8. Okay, so we got this. That's the side length of the middle square. And this is the side length of the smallest square. Okay? Now, if we want the areas of each of these squares, we just need to square the side lengths, right? So the area of the middle square is going to equal x squared, which is x was 8 root 2 squared. And that is 8 squared is 64. Root 2 squared is 2. So that's 128. Okay? And then the area of the small square will equal y squared. And because we called y the side length of the smallest one. So that is 8 squared, which is 64. Okay, and in fact, yes, we keep having, because 16 times 16 is 256, right? So the middle square, its area is half of the original, and then the smallest one is half of the middle one. Okay, are we good? Yeah, all right. Let's keep chugging along. Okay, so this, what do I want to do here? Hold on a sec. I think I am going to talk about adding and subtracting, and we'll have some time to work on that practice. The next couple sheets are just practice for yourself. But we actually you guys did quite a bit of practice on your own. I didn't go through each example. So I want to talk a little bit about adding and subtracting, because it's not too much of a stretch from what we've already done. And then we'll save the last piece, which is on rationalizing and multiplying and stuff like that, for tomorrow. Okay? So we're kind of like at the bottom of page 5. Okay? Adding and subtracting radicals. Adding and subtracting radicals is very, very similar to collecting like terms in a polynomial. Okay? So the idea is that if you have two radicals with the same radicand and the same index, you can collect those together and simplify. Okay? So for example, if I had 2 root 3 plus 5 root 3, that would give me 7 root 3. Okay? So like radicals must have exact same index and radicand. Okay? So for example, this kind of thing would be like. So the cube root of 7 and negative 4 cube root 7. Okay. 6y square root of 2x and negative 3 square root 2x. Okay, so in both of these cases, index is the same. We're looking at cube roots, and radicands are the same. We're looking at radicand of 7. In the second case, we're looking at indexes of 2, and the radicand is 2x. Okay, unlike would be something like this. The biggest mistake that people make, honestly, is something like this. The square root of 5 and the cube root of 5. A lot of people, because we tend to, I do this, and I wouldn't be surprised if a lot of you do this. You do this as well, is that you work really quickly. And so when you work quickly, you start to pay less attention to detail. And this is one of those little details that you might miss, right? Or, I mean, the other one is something like the 5th root of 7 and the 5th root of 8, right? Again, this one, there's more of a stark difference between these two because the actual big numbers, the radicands, are different. So they can have the same index, different radicands. They're not considered like, okay?
Any of the, what are they called? The numbers before, I can't remember.
Right, it's kind of like a coefficient,
Coefficient,
right?
that's what I was looking for,
Yeah. Those don't matter.
Oh, they don't matter.
Nope.
Cool. You
Right.
add them, subtract them.
Yes. Now, when you have like radicals, you can add them together or subtract them. Okay? Okay, so just as an example, I'm not going to do the second one here because this business about 6y negative 3 also gets into factoring, so we won't worry about that. But if I had the cube root of 7 minus or plus negative 4 cube root 7, okay, think about like the coefficients of each of these. This is, oh man, oh, I think I can just do that. There we go. This is almost like 1. I have 1 cube root 7, and I add negative 4 of them. How many do I have? Negative 3 of them, right? So this is negative 3 cube root 7. It's very similar to doing x plus negative 4x is negative 3x. Okay? So this is addition, subtraction. Okay, now I want to do these 4, and then I think what we'll do is we'll stop there for today. Yes?
Just to double check, is it just the radical that stays the same? The coefficient's the only thing that changes.
Correct. Yeah. Okay, so something like this, 8 square root 7 minus square root 7 plus 2 square root 7. You just add or subtract those numbers on the outside. Right? There's like a 1 there. So 8 minus 1 is 7 plus 2 is 9. I have 9 square root 7s. Yep.
Can you turn off the lights after?
Is that better? Okay.
It's so much better.
Remind me to do that next time.
My head's counting all the
Yeah.
way, so this is nice.
Okay. So this next one, I'm adding and or subtracting 4 radicals together. A couple of them are like. So I've got these guys and these guys. Okay, so I can use those numerical coefficients to combine them. So 3 root 2 plus 5 root 2 is 8 square root 2. And then 5 root 3 minus 8 root 3 is negative 3 root 3. Make sense? Okay, so let's talk about the next thing that we might see. Sometimes when we're adding and subtracting radicals, might look like we can't do anything, but those radicals haven't been simplified yet. And if we simplify them, we might end up with some like radicals, okay? So in this kind of example, and in D as well, we want to simplify first, and then see if we can do anything, okay? So the square root of 12, that's like 4 times 3. So I can pull out square root of 4 is 2. If I'm going too fast, slow me down. Are we okay with that, with this being 2 square root 3?
Yeah.
Okay, so this ends up being 2 square root 3. This is 2 times 9. So square root of 9 is 3, and then I'm left with a 2. Plus 3 square root 2. And I'm really, when I'm doing this in my head, I'm thinking about what are my perfect square factors, right? Perfect square factor is 9. This is 9 times 3. So I can pull out a 3. And then this is 4 times 2, so I can pull out a 2. Right? Now, again, you can, like what I would do in between is this would actually be the square root of 4 times 3 is 2 times 2 times 3, plus this is 2 times 3 times 3, minus square root of 3 times 3 times 3, minus the square root of 2 times 2 times 2. Right? So when you're strong in mental math, which a lot of you are, you can picture that prime factorization of relatively small numbers in your head. Okay? Okay, so now we do have some like radicals, right? So these guys are like, and these guys are like. So 2 root 3 minus 3 root 3 is negative 1 root 3, or just negative root 3. And then 3 root 2 plus 2 root 2 is 5 root 2. Okay, and then finally, this is already simplified. 4 root 3 is simplified. Okay, 20 is 4 times 5, 2 times 2 times 5. So I can pull out 1, 2, and I'm left with a 5. So 3 times 2 root 5. Root 12 I actually already did over there. It's 2 root 3.
Why don't we just put 6?
You can. Yeah. So root 12 is 2 root 3. Okay. And then this guy, 45, is 9 times 5. And 9 is 3 times 3. So I can pull out a 3. So plus 6 times 3 root 5. And yeah, if you want to multiply those numbers on the outside in the same step, you can. Okay, so what I have is 4 root 3 plus 6 root 5 minus 2 root 3 plus 18 root 5. Okay, and then all together, I have 2 root 3s plus 24 root 5s. Okay, so far so good? Okay, so I'm going to stop there for today. We're going to talk about multiplication and division of radicals tomorrow. What you can work on, though, for the last 10, 15 minutes is you could work on this pages 3 or 4 to 5, rather. Okay? I don't think I actually remembered to put the key in here, but the completed notes are online. So you can go through and look at this whole booklet all filled out, and you can get the answers that way. Okay?
Do we need to finish this?
Well, work on it in class.